This video, we will continue our discussion of section 2.4 and 5 with another example of solving an exact equation. So, looking at this equation, I'm going to move some things around to make myself feel more comfortable. So 2xy squared plus 4, I'm going to put that together, and the first thing I'm going to do is rewrite that y prime as dy dx. All right, and this is how I'm going to make myself feel more comfortable. 2xy squared plus 4. I'm going to have the dx here. I can multiply both sides by dx, and then I'm also going to subtract that whole term over to get dy equals 0. Now, to me, it looks like an exact equation. Our book, or the source I really pull from, has dx. I think Sasha Townsend also puts a dx under there if you've had her before. So we have that now. So now we actually have two functions we're looking at. We have mxy, so we got 2xy squared plus 4. And how I keep this straight is that was the one with the dx, so I really would like to find the partial of the other, so y. So the 2 comes down with the 2 there, and I get 4xy to the first. And then that's just a 4, it goes away. I also know the other function, and we take the sign with us. So it's going to be a negative 2, 3 minus x squared y. I'm going to go ahead and multiply that out because it's going to be much easier if I do. Oh, I forgot the 2. There we go. All right, and I want to find that partial. Since that's with the dy here, I'm going to find the partial with respect to x. So the partial with respect to x, I get 4xy. Notice these two things are equal, so we get that the dE is exact. I'm going to mention this now so I don't forget it. We did in the last example, I forgot to mention what this thing is, the interval of validity. We'll talk about that when we get there. I'm just going to say it out loud now so there's a chance I remember. All right, so we have those two functions. We know the dE is exact. So we pick either one we want. I usually just always take m. And I know the function that I'm trying to find, that gamma. So let's be a little formative here. So gamma, the function I'm looking for, I know that I can take the integral of m with respect to x, and that will get me back to it. So I'm going to plug all that in. Integral of 2xy squared plus 4 dx. All right, I integrate, I get x squared y squared plus 4x plus c, 1. But we don't use c. Remember, this is a partial integration going backwards. We actually introduce a function of y because there could have been some y's without x's. So I'm going to put h of y there. Now, we can take that, and we can take our gamma and take the partial of y for that. Now I do that, I get 2x squared y. The 4x is gone, we get h prime of y. But remember, we know this is equal to n, right? Because n was also gamma of y. So looking back up there, n is negative 6 plus 2x squared y. Notice the 2x squared y's are on both sides, so those can go away. So I got h prime of y equals negative 6. Remember, if the other variable doesn't go away right here, you messed up. This tells me it's nice, easy integration, so I'm not even going to show it. I got negative 6y plus c. Okay, now I have hy, so I can write what gamma is. So gamma xy is equal to x squared y squared plus 4x plus hy, so it's minus 6y plus c. But remember, and I'm going to call this a C1, let's do that. This tells me now that I take gamma, I know that product rule of gamma will give me the functions that are on the left side of that dE. So I can write the whole left side as this product rule. And it's still equal to 0. Like we're literally jumping now with all that work. We jumped from right here all the way down to right there. We found the function that would work out that if I had a product rule, I could do that with. Okay. So we have that now. We just integrate both sides. We don't even need to show that. It's easy to see. I get plus 4x minus 6y plus c1 equals the integral of 0 is c2. It's another constant. So this gets me x squared y squared plus 4x minus 6y equals, and I'm just going to make it a new constant, c. Okay, now we have an initial condition. I just looked at my notes to grab it. Using the initial condition y of negative 1 equals 8, we'll plug all that in. Okay, we got negative 1 squared, 8 squared, plus 4 times negative 1, minus 6 times 8 equals c. If you plug all that into your calculator, you get 12. So I know my answer is x squared, y squared, plus 4x minus 6y equals 12. And that's my answer to my exact differential equation. Now, they said interval of validity. What this means is we need to just check everything that we can plug in. And then we have to say where we could plug that in. I'm not too concerned. This won't be worth very much on a test. I'd be more worried about can you solve the DE. The interval of validity here, so let's go through our problem. Well, we started out with nice pretty polynomials here. I can plug whatever I want into that. I can plug whatever I want into this. I'm not really dividing by variables. I don't have any logarithms. I don't have any square roots or anything like that in my whole problem. So the interval of validity, because nothing is keeping me from plugging in whatever I want, is all real numbers. So what you're looking for is you look at the beginning of the problem, you look at your phi, and you decide what you can't plug in there, and you look at your answer and decide what you can't plug in there, and that'll tell you your interval of validity. Not too important at the moment. That kind of stuff will become more important when you started applying it in your actual topic courses that are applying your mathematics to your sciences. So there we go. That's another example of an exact